Hello, guys, and welcome to A.M Learning and welcome to Kaggle Days Meetup. And today, in this Women's September series special, I have Sharmistha Chatterjee with me. She is the senior data scientist, AI mentor, Google developer mentor, and she has been an inspiration to many. When you follow her LinkedIn and post, she's been doing amazing, and it's so great and honor to have her with me on today's live session. And before we go ahead, I'd like to thank our community partner Merge Intern for helping us with and reaching out to students. So it's such a great morning, and I hope you like today's session. So I would like to welcome Charishmita today.
Hi, Manpreet. Thank you for the
Hi, good
introduction.
morning.
Good morning. Hope you all are doing good in the COVID times. Before we get into COVID analysis, yeah. So
And so, what made you start data science, and why did you choose data science as your field?
Yeah, so I primarily don't come from data science background. I was a hard C++ device driver programmer to start with because I started my career in 2005. That time, data science was not there. So I started slowly moving to data science when I did my masters. And that time also the algorithms were like clustering were coded in C++. There was no library. So only MATLAB was there. But if you want to put in production, you have to code in some language. So we were doing in C++. Then slowly I got to work in one or two projects with data science, and that's how I started to build my profile because I was doing a full daytime job and then putting myself up to speed. It took a lot of effort, like putting GitHub, studying different things, doing some courses in Coursera, seeing their examples, and that's how I started to move to data science. So slowly I moved it, and along with that, I think I was also fortunate to have some cloud experience, so that also helped in my journey to put the codes, data science models to production and see how they are actually working, affecting the life of people with real predictions.
So I have seen lately, like you have been working for community and taking up sessions. So how do you manage with this busy schedule and taking up sessions on the weekend? And how do you feel about working for the community? And
Yeah, so every time I think that next weekend I will not have anything, and I think I see something is coming up. So it was hard for me to say no. So I just take it and see that okay, take 1 hour I will manage somehow. And I look forward to the next weekend thinking that there won't be anything. It's a bit challenging because I somehow put two of my kids with my helpers who help me a lot. They are my prime support, and my husband also supports me during this time when I take off in the weekends, like a 1 hour session. And and for that I have to prepare. So whenever I am writing blogs or all, I try to do something different than office work, so that I also keep learning along with it and try to help the community whatever I have learned. So
so,
that's how
how do
it
you
is.
think important is? Yeah. So, how important do you think is writing blogs help, or writing some posts that you have learned and you put up it on LinkedIn and share with people? Like, I think people don't know much about blogging and stuff still in the field of data science. So, what are your opinions on it?
I think it is very good, and if you like very introductory blogs, that are going to get a very good hit because people once start learning some very introductory stuffs, but think it is something different. But people has not just before writing, just Google it and see that people have not written something. Even if they have written, you give a different perspective of seeing that problem. So just differentiate between two different libraries, basic things. So it can be a 2 minute to 5 minute read, and that will help you to build a good profile and put some simple code in GitHub. That's how I started. But then I felt not to write very introductory things. I got shifted to a bit more in details because that was helping me to learn. So that is one of the reasons I don't write very introductory things, because I thought that I got the knowledge of it. But if somebody who's starting, they start with introductory things, and add some new perspective to a problem which has people have not put it, anything like profiling the code. So you are doing some metrics computation or something. So what's the time it has taken to do that? So simple thing, so that will, I think, boost your knowledge also, and it will help also to in the longer run. It's very
Okay,
important.
so yeah. So now, without any further ado, we'll start your session. But just before starting, I would like to say don't forget to like, share, and subscribe to our channel. And we have been coming up with awesome meetings held this month and ahead also. And go follow Charishmita. I'll be linking her descriptions below, and follow our community partners as well. So all ahead your session, I hope to learn at the back end everything that you are going to tell today.
Yeah. So hope you can see my
Okay.
screen.
Yeah.
Yeah. Okay, so since Manpreet has
Yeah.
given an introduction, I won't spend a lot of time on it. I have put all the references where you will get it in my blogs or in GitHub. So let's start with today's session. So what are the key takeaways that we are going to have today? So mainly the basic, I will start with why time series modeling. What are the basic mechanisms of time series modeling? Then we'll slowly dive into deep learning methods like RNN, CNN, LSTM. How do we develop time series model with this, but using sequence to sequence learning? And then we'll see with notebooks and with real examples like COVID-19, for both for univariate and also for multivariate and multi-step analysis, that how it works. So it may be the notebooks, maybe the multivariate multi-step analysis may be a little bit confusing, but I will try to make you understand. And you can, anyways, these are available in GitHub. I've provided the GitHub links. You can download and see. And if you're stuck, let me know. So I'll try to make you best understand the make use of today's session. So why do we need time series? What are the applications? So you see, everywhere, like financial market, budget analysis, projections, military workload, everywhere economic forecasting, we need time series. And we discover trends, seasonality, cyclical patterns, anomalies, and critical event analysis, as well as different cause and effect analysis with time series modeling. So here is all the applications, and here is the criticality of events. We have discrete events or continuous time series events, like which are not discrete events, means different values, like is something like you say number of deaths. It's not continuous. It's number 1 or 2. So 1 to 100 discrete value, but a continuous like ECG. So all the things can be done with time series analysis, as well as you will see causal effect analysis. That is, I just introduced the term. There is a causal AI library introduced by Google that also depends on time series analysis, that's used to find the effect of any campaign on a market, on a particular product segment, on a market. So that's also based on time series, but it's done in a different way. So you can look at Google video for causal effect analysis. Now let's see what are the different what are the statistical methods available, how are their errors, and what we can do with these modeling techniques. So the supervised techniques you will see autoaggressive moving average, MA moving auto AR, MA moving average, arima, sarima. If you have not heard of the terms, we'll come into the detailed terms. Autoregressive integrated moving average with seasonality, sarima. Then unsupervised time series, traditional mind series, you can use clustering. Yes, time series can also do clustering, segmentation. Okay, that is to find the nearest neighborhood in terms of time, what are correlated to the actual neighbor. So in this context, I will give you an example of IBM, what IBM Watson has done, but I won't go into the details of it. If you have time, we'll go. Otherwise, I'll leave it to you. Everything is there in the slide as well as references. You can understand when you are digging a little more in details. Then we have deep learning methods, deep learning, univariate methods, multivariate methods, and with single step and multi-step. What is single step and what is multi-step? Single step is means you want to forecast in your future. It can be 10 days, 50 days, or 60 days, 3 months. And what is multi-step? Multi-step is you want to predict, say, nearest say 6 days or 7 days or 10 days, and you want to use whatever you have predicted for this nearest 6 or 10 days and feed it into your model, and you want to predict for the next 7 days. So first you predict 7 days, use this prediction and put it in your model, feedback to your model, and use that to predict the next 10, next 14, next 7 days. Means after 7, the 7th to 14th day you want to predict. So that is with multi-step analysis. Okay, and here we have the different error metrics. On the left hand side you see which are the methods which are giving very good results. So you see like the arima, damped methods, these are the statistical methods that they give a good, it's a robust mechanisms of estimating time series model, provided they are done on they are more of a linear relationships. They try to develop it's regressive, they have regressive terms, so they more try to discover linear relationships in the predictions. So there are mechanisms of doing nonlinear predictions. I'll just show you the libraries. So we have talked about different types of different time series modeling. We have Markov chain also that learns stationary distributions over state space, but they are not applicable for drifting systems for multi-step. Okay, arima sarima, we know that they can compute a function of finite paths, means it cannot be infinite, along with some noise. So there are dampening factors. We will see how we can put a dampening factor to model the time series. Then we have exponential weighted averages, exponential smoothing averages, so that can be applied to trends. That can be this one exponential, if you see, that one can be applied to trends, levels, as well as different seasonality. Okay, seasonality by when I mean by the term I mean that so for if you see a discover a pattern over a next 4 months, every quarter you see a pattern, or every month you see a pattern, so that can be used, that exponential smoothing averages can be used. Exponential smoothing have different types, we'll see, that can be used to model the different weights. Like we can put a higher weight to recent data and a lower weight to past more data, so we can use that to model the time series. Then you have Hall-Minter model. So in addition to seasonal components, it also has level and trend. We'll see how that can be used, and there are two different versions of Hall-Minter model, the additive and the multiplicative. Then we have, as we have discussed, there are unsupervised techniques and deep learning techniques. So here you see a graph more on the right hand side, like purpose of the forecasting. Like we have to understand how important it is to provide to forecast the dynamics and components of different time series modeling. So you see long-term trends is there. These are the lines for long-term trends, and these are the trend for cyclical. This is a cyclical trend, and we should also know the term lag in time series modeling. Why? Because when we compute arima, sarima, or seasonal order differencing, we should have a difference between like what happened in the past and what is the present. So what is the lag factor? So it is a lag of 2 or lag of 3. What is the lag between the corresponding components between the current and the previous past? So lag factor, we have to find out what is the lag happening in the time series by differencing it. And let's see, these are the unsupervised feature learning techniques that have different forms that we try to find out through clustering techniques or segmentation. And you could find that there are different shapes which we are discovering. And this is the most commonly used term, RAND index, which is used for discriminative feature shapelet learning. So these are some of the terms I'm introducing so that you get familiar before we dive into the problem. And now we have talked about the simple exponential and Hall-Minter model. Let's see what is simple moving average. So simple moving average is you try to find a relationship between a current, you try to model a time series with the current instant and different lag factors or errors that has happened in the past. But the moving window, simple moving average, there is no weight factor associated with it. So there can be a constant window, like current time is equal to the previous time plus the previous minus t minus 2 minus plus t minus 3 divided by number of terms, p. Okay, so this is simple. There is no weight. But when you talk about weighted MA, you can see here on the right hand side, I've put 1 by M and W1, W2, different factors. Like if the recent data has more weight, or the next data has a little bit less weight. So how do you model the weights? That is weighted average. And then you have simple exponential moving average. What is simple exponential moving average? This is nothing but you want to have a decay, right? To put more weights on the current term and less weights to the previous t minus 1 terms. Like a t plus 1 you are predicting, t has the highest weight, and you slowly you can put n time instance and corresponding with n weights. So your weights might decrease over time. So you have a decay like over the weights with time. So that is an exponential. Why it is termed exponential? Because first is you put more weight, then you say less. So there is a decay like an exponential function. So you also have double exponential time series, triple exponential. So and both of this has dampening factors, additive and multiplicative trend. So additive trend and multiplicative trend will help you to decide how do you decay the curve. So additive will be will be more linear decay of the weights. Okay, because it is exponential, so it has to decay. It means it has to increase or decay. So in an exponential manner, additive will be a little bit linear. It's not too exponential. And multiplicative will be because the weights are multiplicative of the previous one. So it will be a very exponential decay. And then you have when you talk about triple exponential, you have seasonality. You have to define the steps where are the seasonal factors coming into play to analyze the time series, as well as both of them has dampening factor. And these are the equations. Let's not go into different. I've just put it so that you can refer to it, that how is label defined, trend, seasonal, forecast. Let's go and spend most time with the notebook instead of going to the equations. So additive is less variation among the different among the seasonal factors in the time series, while multiplicative has more increase. So here see, additive means it's increasing, but multiplicative is more robust, and multiplicative has a trend, like a more visible trend. If you see, it will increase more visibly than the additive. So additive is not that much useful if you think of deriving a robust model. And here we use more of absolute terms in terms of increase or decrease, and here we use relative terms. So we'll see how we can do it with actual code. We can say additive or multiplicative seasonal factor that is affecting it. And this is arima. And so just use the basic concepts like P, Q, and D. So P, Q, and D are the orders that you have to derive from an arima model. And how will you do that? So for arima, ARMA, and these two combines and gives us the term arima, auto-regressive integrated moving average. And while you have an auto-regressive moving average, you can use the state space libraries in Python, and that to decide by manual selection or auto selection the PQD terms. PQD terms are nothing but number of lag observations, the number of times the time series is differentiated at D, and the Q, that the what do you call the MA, that this is the regressive term, this is the MA term, and this is the order of the term. And how do you do that? You have first you have to do a ACF PCF plot. You take the model, you import the libraries, you take the ACF PCF plot, find out the difference in term, that is the D. excuse me. Then you, once the time series is stationary, sorry, yeah, you conclude on the best P, Q, and D, like 2, 0, 1, 1, or 2, 2, 2. What are the terms that you are going to use? Obtain the BIC. There are metrics that define the Bayesian information criteria or A.I.M information criteria. They define how the model in terms of entropy or or on the Bayesian information criteria. So how the model is behaving in terms of this metrics or the accuracy. You can even specify that accuracy. And if you're satisfied, then for or manual modeling, you see that the residuals when you residuals are nothing but errors from previous step and the current step are resembling white noise. You are satisfied with that model, you compute the different error metrics and gets here you can freeze the model. But if you're not satisfied, you have to tune the PQD factors to arrive at a satisfaction level. So but auto arima, whereas I'll come to that side, if you see auto arima, what it will do, it will allow you to determine the PQD terms automatically in comparison with arima. Okay, and AutoArima is a very well-known library that will do itself the hyperparameter tuning, and you will arrive at the best PQ and D metrics. For the AI model is nothing but it gives a relationship, that is the P factor, that is the relationship between the different timing instance. The MA model, that is the lag factors, that is the different previous times. The MA is the residual error. MA is previous times, what are the error which has been obtained. Okay, so and this has relationship, the current time instance is a relationship of the error factors of the previous time. So you see here these things are the epsilon is coming here. Okay, the error metrics are coming here. And arima is a combination of AR as alpha and beta and the error term. So it is alpha beta plus the error term coming into, if we take both of them. And what are the libraries you use? So for univariate auto-regressive time series, use TSA, their state space model. You can use that also. So that are more for irregular components. This is for more regressive terms which are linear, some kind of linear prediction. And vector AR, which is used for modeling and analyzing time series, which is you have to have a lot of exogenous factors, lot of time series modeling, use vector AR. And same for Sarima. Sarima also, Sarima with auto AR, what you will do, you will have PQD into capital PQD. What is capital PQD? So seasonal auto-aggressive order. So Sarima means that you are considering seasonality in your model. So you see whether it can, and you can specify there will be an M factor. Then now, so that will specify where the seasonality is repeated over 12 months period, like a year or a month or 2 months or 4 months. What is that? That is the seasonal factor. And then the Q factor, as we have discussed, is the moving average factor. But here, this capital Q signifies the seasonal moving average. D is the seasonal differencing order, and P is the seasonal autoaggressive order. So, and another important term which we have to introduce in time series context is the Box-Cox transformation. So this is helped to make a more uniform normal distribution before applying arima or sarima model. So it is like kind of like a log order transformation or a power order transformation that scales down the time series, and it yields a more normal distribution. Then you can apply auto sarima on it, check the metrics, resemble white noise, and you are satisfied, freeze the model, compute the MAP, whether it is the mean absolute error, mean percentage error, or the RMSE and mean absolute error. So these here you don't see that there is an arrow going back again to decide, because your auto arima does the hyperparameter tuning. Here you can specify the max Q, the max P, and the max D term. So from it's starting from 0 0 start P, start Q, and to the max D, it will do all the grid search and it will find out the best parameters P, Q, D for your model. Now let's see something in action. After this slide, we'll go to the notebook. So then you have the autocorrelation clause, because you have seen that first you have to come at the right D. So you have to make a time series stationary. And how do you do that? You have to apply this kind of a function. Like what I have done is, per state I have taken the number of active cases and done a first order differencing and second order differencing. So second order differencing, you see here all the values come closer to 0. That means this time series is stationary. So first order differencing does not make the time series stationary. So I cannot choose and fix D as 1. We have to differentiate the time series again to arrive at D is equal to 2. This is the code for that. So diff of diff to get D is equal to 2. And And this is the Varmax model. This I have not done for COVID-19. So Varmax model, you can have multiple parameters. Like these were, I was discussing more of univariate. Varmax model, you can see equation, temperature, wind speed, different factors, different residual standard error, and this is the equation for that. And you have to plot the diagnostics and understand what is the best model for you. Now let's go to uh, uh, the notebooks for COVID-19 before I come to deep learning. So if you go to GitHub, you will see first what I have done in the GitHub. There are like the data discovery I have done. Then I have done some kind of a prediction using this standard libraries like the Hallwinter, Arima, Sarima, all this forecasting. Then I moved to multi-step forecasting and single step forecasting with deep learning. So data discovery is nothing, but I have taken data from stats. There is a website called, I don't remember the website name. The stats, some I have, yeah. So from here, yeah, I've taken the data. So I've tried to understand what is the impact of for different states. I've taken the data and tried to understand the impact of literacy, different effect of number of international airports, the number of passengers passing through the international airports in per day. So what is the impact of them on the COVID-19 data? Then we have done the zones also, but these are more of a constant value. So zones where when I did this modeling, I got zone information on it was done on June. So it was more of a
Charishmita, can you zoom?
yeah.
Can you zoom the video? Yeah.
Can you see? Yeah. So international airports, number of passengers in busy international airports. Okay. And population density. Okay, these are the terms which I've got from this website. So taken this. So these are more of hard coding the values. The aging population. What is the aging population? That is per state. Okay, number of hospital beds. So these were constants. I will come into where they were dynamic. So don't worry why these are constants. These are constants because for a particular day I choose to start with the process. Ventilators per state, number of ICU beds per state. And then what we have done is you will see some plots. So these are some plots. I have to, yeah, total, this you will see everywhere, total confirmed cases. Then with Plotly, I have done the active cases per state, which are the states and what is the plot with date per state. So remember that you have to always index your time series. Whenever you're plotting against time, that is one important thing. Your X parameter, means the X-axis parameter, has to be properly indexed with the dates. Okay, so now you have the dates. These are normal things. Then let's look at recovery, population density. So you see Delhi has the highest population density, and that time was Delhi was also recording the highest number of cases. Then we have Pondicherry, all the factors like plot literacy rate. Literacy rate, Kerala has the highest literacy rate, and that time also when June, July, Kerala was experiencing a low surge in the number of COVID cases. Elderly population. So, and then we draw I don't go into details, you can always look at it. So hospital beds, ventilators, ICUs, everything is there. The correlation map. So what is affecting the COVID-19? So when you see the deep blue, the deep red is the high correlation. So if you see deep red marks here, what is that? So if you see this, cured, discharged, and migrated has a high impact on the number of active cases. So this is number of active cases. The number of deaths and the total confirmed cases and active cases. This you can also understand from the data. But what are the other factors? So you see the other factor, you can these oranges, you can say number of red zones. So number of red zones is closely linked with a high number of active cases. Okay, this is number of red zones. These are number of red zones, districts affected. They are more related to number of active cases, number of deaths, and these also have higher number of state hospitals, hospital beds, because the cases are rising. So hospital beds were allocated, the ICUs, ventilators were also increased in those places with red zones, districts with high number of districts affected and number of red zones there, and as well as orange zones also found. But when it is very low correlated to green zones. Okay, and then also international airports, it has relationship with, that's why it's red. A big orange means correlation is decreasing. International airports, international airports, and we have discussed about the ventilators. So these are also highly correlated. Ventilators, state ICUs, hospital beds. Okay, so now we will do some modeling. So modeling with, yeah. So that what we have discussed about simple moving average, exponential, different regressor terms before moving into deep learning. So here just I'm plotting them. So I have got the data of all the states and then split it up into state wise. So there is a features folder. If you go to GitHub, you will find there is a features folder. Inside that I've put per state data, and then you see
Um,
here it. Can you see?
yeah.
Yeah. So this is just simple plot of active cases, just doing the simple exponential. Let's move into simple exponential and Hall's mentor prediction. So this is univariate. So I'm trying to predict the active cases, okay, based on previous data of active cases. So a time series which is trying to predict the near future based on previous data. So there is a smoothing level, as we have talked about, that how do you smooth, and these, remember, if you correctly choose the smoothing level, smoothing slope, like how do you time series is, it's very fluctuating, so you may want to smooth it a little bit. So these factors you decide, and if it's select the right factors of smoothing, along with you have also have damping factor, you will be able to make the curve straight, means the flattening of the curve. So that's what was a big topic, when our curve will flatten. So this is frequency is day, every day, that's why I write frequency equal to day, and then the percentage of test versus trained data. Okay, and this is how, this is the prediction. So the prediction is going, I have chosen the smoothing level like that. You this is the validation data is, you have trained data, validation data, test data, and this is the, if you see, this is more closely resembles the original time series, where the test predicted data is showing that the curve is decaying. So you have to correctly choose the smoothing factors and the dampening factors. So see, this is the alpha. So a smoothing level and the simple exponential. We still have simple exponential time series and smoothing level and smoothing slope. That is the, what is the slope of smoothing it. So if you correct select those parameters, and you can try to find out what is your decay and when your time will flatten. If that is, then accordingly, if you find out the smoothing level and the dampening slope and these factors, like what smoothing level, slope and the dampening slope, then based on that you can say that if there is a decay of at this rate, your time series curve is going to flatten. And this is like what I talked about, like the indexing is very important, because you have to plot against days. So your x-axis is the number of days, so that has to be properly indexed. And you see here, so I'm trying to decay the curve and make it flatten. So I have to choose some smoothing factor, dampening slope for doing that. And if you see there is an exponential rise in case of Maharashtra or Delhi, then you have to be more proactive in choosing the right dampening factor and the right sloping factor, because this is a steep rise, right? But Kerala was already decaying, so it has just smoothened out. So it was done during the month of June. Again, there is a surge, so that is not taken into account. So Hall's winter linear model is there, and Hall's exponential model is there. Just you have to select the right parameters, and remember these are univariate. Okay. And this is again, see this one, Hall's linear trend is more, and the predicted trend. So that's more giving a rapid decay. And the exponential trend is also decay, but it is more like it has continues to stay stagnant. And when you have added dampening factor, like it's dampening, it's just dampen factor, after time it will become stationary, it won't decrease. So while linear is decreasing, because there's a relationship, there's a linear some relationship, it will decay, it will continue to decrease. Exponential also, the weight factors decreases, so it's trying to decrease more here, but whereas dampening has become stagnant. Now you plot all these things, and you can measure the level, slope, and all the parameters that are used for that you have used for your hyperparameter tuning or whatever slope you have selected, and plot it and see it how it looks like. For this is for like the number of days. This is nothing but the number of days. And then you have for Delhi, same thing. I've done simple exponential smoothing, exponential smoothing, and same thing, active flattening of the curve. I tried to do like when it flattens, and that time it was like June, July time. So if you correctly select those, it will get stagnant at a time. And then winter series, same thing for different states. I don't go into details. And you see regression models. So apart from this, then we will move into arima. There are regressive factors that helps you to select the correct parameters, means that helps you to correctly predict it. So here I have taken literacy rate, districts affected, but these are more of constant values. If you get more dynamic values that we will do with deep learning, you will get a more accurate variation of it. So linear regression is nothing. You try to predict the number of active cases with linear regression, split up the data, train and test data set, and plot it. So just linear regression dot predict. Okay. So it just follows the active cases and the predicted cases just overlapping each other. Is very giving good results, but it is again you have to think that it is a univariate time series. Okay, you can allow a polynomial regression, that is that you can use lasso, you can use elastic net, ridge regression, and you can use a pipeline to along with this I have used ridge regression. And with the what is the order of your regression, like 3, like it is a like 2 to like x square or x to the power 3, what is the factor you are using, that you have to specify here, and plot it and see how it is behaving. So these are most straight. I've done it for different states, and then same thing. Then let's move to arima sarima. So additive you can do, multiplicative, so and see the differences. What is the say exponential is like the standard errors are more, the alpha the alpha beta, these are the factors which we have seen, the trend, level, slope, different factors we've seen in the slide. So map them, like what is the alpha. Exponential factor has more like alpha, and but beta is less, and I0 and B0 are again more, for because it has to decay more rapidly. And then additive and multiplicative. See autocorrelation text with this, you can see where is the plot coming to 0. Here it is coming to 0. So after 50 terms, after say 30 terms, it is coming to 0. I can print the p-value, the critical values at different levels. What are the critical value of Dickey Fuller test? So not go into details. Then I'll look at arima model. Yeah. So arima. So first is AR term. Okay. So AR is the regressive term. So you think of PQ and D. Okay. So first term is the regressive term. Put it 200 only arima. So plot the residuals, see the residuals, what is how it is working. So what is the standard error, what is the coefficients, it is using the regression coefficients, and see the plot. So this is the plot for AR. This is the test. This is still this is validation. This is the test data set, the predicted data set. Okay. Now MA is again PQD. So select the collect which state you want to do. So I have created like a map kind of thing. I will pick the state which I want to do. 70-30 split, train test data set, and then it is the arima MA term. So rest was 0. So I term is 0, P term is 0. The Q terms for MA, like the moving average. Okay, it is a slightly different. So if you see this plot compared to the previous one, see MA moving average, it has dropped down. Same data. And now we use 3 terms, arima, A111. I have used. You can use 222. So see how that curve is behaving. Only you have to write one line of code. You have to select the variable and select the correct order, fit it, feed the model, and forecast on a validation data set, and then put it in your result and plot the residuals. So when you plot the residuals, you get all this information metrics like coefficient, standard error, and you also calculate, plot it, and plot the standard error of that RMSC. So I have plotted for Maharashtra, same data what we have done for arima. So this integrated moving average, when you use it, it is a better than MA or AR. So you have used both AR, MA, and integrated moving average. Okay, and then you should also compute the RMSE of the each and individual curve what you have plotted. That is the predicted minus. If you have the actual data, I couldn't compute it because the actual only the validation data I can compute, and the test data I don't know. That time it has not come. I cannot predict. I cannot compute because it is going to come in future. And sarima is apart from the order, this PQD order, you have to specify the seasonal order also. So there is no seasonality in COVID. We have, because we have not arrived at that point. I don't think there is any seasonality. But I have tried to put 12 and see what's happening. You have to put some things to see the impact, what is happening. Only then you conclude that it has no effect. Okay, and the root mean square error for the validation data. So only for the validation data you can compute. Okay, and compute this, and you can compare between different models what is happening. And here is the sarima. Then same thing for auto arima, as we have talked about. Auto, you have to also compute the ACF and PACF plots. So that's the code for here. I put it into the slide. Autocorrelation plot. So zero, that is you do through differencing, difference of differencing, because it is order of 2. Okay, drop the NS, plot it, because this null value is of no use. Okay, so now you see the order of 2 that you decide that D. And then when after you put the autocorrelation, you can also plot the partial autocorrelation. So partial correlation takes some of these factors into account. Autocorrelation takes all the factors into account, the regressor terms. Then after that you can also do same thing, seasonal differencing. So seasonal usual differencing and seasonal differencing. So there's no seasonality as such. So it is closed loop. It is taking a little bit, but I don't think there is any seasonality in COVID data as of now. As of now. Now auto arima, what we have discovered. So you can specify start P, start Q, max P, max Q. What is that? So start PQD we have discussed. So PQD, you can ensure the start values and the maximum values. And then it has the values like it does AIC, BIC factors is compute and tries to give you the best model. So it has decreased here. See, here AIC, BIC is the best metric what is available. So it has freezed. Now it's stopped. Let's stop because we have arrived at the base metric. So 520. Have not taken seasonal. Again, this is the seasonal PQD and M. That is what is your M, like the seasonality number of steps, 2 months, 4 months. So residual plots, root mean square, and the actual plot with auto arima. Auto arima, see, it looks much better than actual arima because it is doing the hyperparameter tuning rather than you doing and find it out, and it is finding you the best model. AR, same thing for this is the better way of plotting it, how you plot it with subplots, and you have a boundary between how it can vary. So that's the gray one. Same thing. And then when you do here, it has come freezed here 0 to 5, and that's your plot here. See, this is much better than this is MA, I think, right? This is auto arima with MA. Let me see the plot. MA, yeah, MA. So previously what we see, it has got dropped down, but with auto arima it is much better. Same thing, and auto arima with ARMI. So there is a lot of hyperparameter tuning. So see here, start P1, start Q1, max P, max Q, and seasonal is false because auto arima have not considered seasonality, and it has come here and it has given you a lot of hyperparameter because all the terms are there, PQD, everything is there. So what is the time it has taken, and it is plotting it. Okay, now you can, for next 5 months, you can predict that what is going to happen in the near future, frequency in terms of D, and sarima model. Sarima model, nothing, you have to put M is equal to something you have to put. I have put 12. I don't think there is any seasonality because I was assuming that next time if it starts again, there is a second wave that is going to come. So seasonal you have to put true. M you have to put, seasonal you have to put true. So there is a lot of tuning. And then you see the curve. Closely it resembles arima only. Okay, so now let's move to, there's a seasonal differencing that we have done. first order differencing, second order differencing, autocorrelation, and partial autocorrelation you can also do. So there's another model from Profit from Facebook. So that also I tried it. Nothing extraordinary. And Varmax model. Varmax models can be used for if you have exogenous factors. Now let's introduce the term exogenous factors. Exogenous factors are like something externally is happening. Say there is lockdown. Okay, so there is lockdown happening. Can we measure the impact of lockdown of every individual state and with time? If you can measure with time, or you can fake the data. We can fake the data and incorporate that into our model. So that are not the exogenous terms of that which are not affected by the model, that are external factors which are affecting the model but itself are not affected by the model. So Varmax is the kinds of models that we can do for exogenous factors. So I could not take any external factors. I have done without exogenous factors. So here you will specify the exogenous factors. Okay, I could not measure any lockdown or something, so you can try to incorporate those and put it, just extend it, how the exogenous factors are behaving. So this is the predicted one. It's much like much less impact in the with the exogenous factors. So this is still a future work which we can take it up with the exogenous factors. Now, but deep learning, I have introduced that one. So let's move on to deep learning now. So questions keep on posting. So we can take those. So Varmax models, this is the one you can include, and this is the beauty of the Varmax model is you can introduce multiple terms. Like you can include, say, active cases plus recoveries. Both of them you include, and you try to predict what will be the active cases in near future. Plus, you can include the exogenous factors. What is the lockdown factor? What has happened because some vaccine is upcoming. That is more, it will come right now. So the vaccine is coming, some trials have been done, these are the effects. So these are not actually affecting the model, but these are affecting the model, but it's not affected. Now let's look at deep learning models. So deep learning models, you have a lot of things to do, like you a lot of branches. So they try to find out the nonlinear relationships so that our training models are better, and for millions of data, billions of points that you can scale. So deep learning models are always best. And also you can, from day one, you can introduce exogenous factors, you can include other features, and like we have tried to include so many parameters like this. Sorry, this is corona equity cells, cumulative persons per people in quarantine, test negative, the number of state line helpline numbers, then ICU beds, isolation beds, ventilators, so many things. How many testing are done? What is the rate of positivity in the test? Mass manufacture. So I got this data from Kaggle, and then I tried to pull it in. So you see, you have to do the data clean. Of course, some in multivariate in LSTM, or we are not doing any much of, like, say, feature engineering. But if you can do some kind of data cleaning and data transformation, do that. Like transformation is of course necessary. Standardizing the model, like scaling the model in terms of 0 to 1. So you one feature, if you see, there are 1 lakh cases in some other places within the same state, there is 2 cases. How do you normalize the data? So you have to use the standard scaler or a min-max scaler to scale it between 0 to 1. So we'll see how we will do that. Then you convert the time series to a supervised time series. This is the most important step. So whether you use multivariate, single variate in deep learning methods, or you use multi-step, you have to convert the data to supervised time series. And how do we do that? We take differencing between the t and t minus 1. So t minus 1 you take as the input and t is the output. So that is called, when you arrange the time series for t minus 1, you get the t output. That is called converting the time series into a supervised model, so that you know that for this x input, this is the target variable. So that's all we have to do. That is the main thing. And then it comes to a normal deep learning model. You can do hyperparameter selection and evaluate these models, and you can either use single step forecast, multi-step forecast, compute the error metrics, and if you don't find suitable, you go back to a deep learning best selection strategy. This loop gets excluded. If you can, from here you can select the best model. That will, like auto arima, we have seen that you have found and freeze the best model. If you can incorporate that with your code, no need to come back to this loop. So let's see how do we do that. And these are some multivariate step analysis what people researchers have done, have tried to put how come different factors, number of different factors like clustering and weak clustering, how different time steps from you get different time series data from different sources. So how do you see the different patterns? So you have to use multivariate time series. We cannot get ourselves confined with arima sarima. You have to know deep learning, and for these sensors, think of so much data is going to come. So you see different trends in terms. And now when after motif merging, what is motif merging? So pattern discovery. So this is another very important thing for multivariate time series. So there are different, I won't cover that, I'm just introducing it. So there are different libraries available for pattern discovery for multivariate time series. So you see here different pattern, after motif merging there is different pattern. So just be aware of this thing in multivariate time series. Now let's look at same thing. After they're encoding, doing the motif efficiency characterization, this is more of DSP sizing of different digital processing signals. So they do that and they find out the patterns. Now let's go and do something what we have done for COVID. So COVID deep learning analysis we have done for LSTM, CNN, LSTM plus CNN, and by LSTM. So let's go. The most important thing apart from supervised conversion is the is the reshaping. So how you are reshaping the data in terms of when you feed it into the network for prediction as well as for training. So this I'll come back again. So actually this is what for multi-step. We have talked about multi-step, right? So first you predict for week 1. So 7 days you do the prediction. So you have a one data point which gives from from previous points how many from the past you have predicted for another a week, right? So you have one data point for one prediction. Now that has to be incorporated when you predict for week 2. Okay, so 7 plus 1 8, that is going here. Here 7 days is going, and then these 2 weeks prediction has to go for week 3 prediction. So multi-step is nothing but a concatenation of input features from previous data, whatever your training data set is, plus the nearest predicted data. So here you have the nearest prediction of week 1, plus here you have week 1 plus week 2. So 9 days data you have predicted for this week. What is going to be the after this week's data? What is the prediction? And how do we do that? So we do in different ways. Let's look at this. This is for CNN plus LSTM. So this is, we use convolution 1D. So here you see your how do we do CNN with LSTM? You have to the CNN will take the, while training it will take the subsequences. Each you can specify your number of subsequences. If you see here, your subsequences is this input shape has to be defined, that what are the subsequences. And here we can if you have a step of 4 steps, you can split it. You can split and create your subsequence. So you have created 2 sequences, 2 steps. So and accordingly you have to reshape your model in terms of this. This is the input shape that it will accept. That samples is how many data you are using for your prediction, training data. Then the subsequences means that how many subsequences you are feeding to the LSTM model. So each will be treated separately. And the time steps is we usually use 1, because this time steps comes more for like video processing frames, like you are extracting video frames, like so video frames you will increase 1 frame you have extracted, next time next video frame, and the number of features. So this is a multivariate, you specify the number of features. And how here you reshape your model. Again, your training data has to be reshaped in terms of your number of samples. Subsequences is whatever you define, 2 3 whatever, and how many times you are going to feed it the CNN model. And the time steps 1, and the this univariate, so I put 1. So if it is multivariate, you put colon or 10 features, 15 features, whatever it is. And you have to use a time distributed layer. So this convolution subsequences which are coming in CNN has to be wrapped wrapped with a time distributed layer that has to be fed to LSTM. So this is very easy. LSTM, if you are not aware of deep learning, this is LSTM and this is dense network to get the output, right? It's a regression problem, it's not a classification problem. So there is one simple ADAM optimizer, ReLU activation, and the one dense layer to get the output. But this, how do you feed the data from the CNN, which has so many subsequences, to LSTM? So that has to be done with the time distributed layer. So that's how the convolution, each of the subsequences gets fixed in terms of the time distributed layer and goes to the LSTM. And let's see how, what I told that previously, that the conversion to supervised problem, that is the most important thing. You cannot proceed in deep learning without converting the either the univariate or multivariate multi-step data without conversion to the supervised training. So here we do that. So series to supervised. So in your input is, what is the how do you convert? So t minus 1 gives t. So in is 1, out is 1. So you are not taking like t minus 2 is giving t. So that time you have to space your models accordingly, that t minus 2 will give you t. So your in and out will change, okay, because that you are differencing it. Okay, now shift I. So I is your in 1. So 1 to 0 to minus 1, that means 1. Actually, you're iterating 1 terms. So you're shifting your model by 1. So t minus, say t minus 1, first value, second value, and t minus 1 and second value will come as your output to t minus 1th instant. So that is all about the conversion of time, supervised time series. And then you concatenate and drop the NaN values and return. So this is the most important. If you have understood this step, you will be able to do everything. So, and then when you shift it, time shift, you can do rolling in this. When you do df.shift, you can do an expanding rolling window. You can fix your window. You can do smoothing, MA. You can do multiple things when you do here the df.shift. Many different things which we have talked about, like expanding window, rolling window, MA, that you can do in top of this. And for multivariate, this is for multivariate also. This is single step multivariate. This is single step, and this is multi-step. So what is happening in multi-step? In multi-step, you do the same thing, but you have to be careful that your output, but this each processing output in terms of is in terms of 7 days. So it can be anything. I have put 7 days. So I am predicting per week. Okay, so that you specify, and accordingly your input data is accordingly splitted up. So you have the input. So your in will be start plus n output. Okay, 7 days you took, and from the next point you split it up. This is the in end. Okay, so your data in start plus in end, but out is in end, wherever you end it, and this is your out end. Are you getting? I'm not sure. This you have, if you dry run, if there is a board, I would have explained it better. So first 7 days is your input, and from 7 day to next 7 days your output. Here what is happening? Here is your in out is 1. So today is your input, and whatever you are getting tomorrow is your target. Okay, only 1 day shift. But here, because it is multi-step, so I take trend 1 week, predict for next week, then, and that week prediction is again used to predict a value. That week's prediction, it has to be appended to again this data to predict the next week, second week. So 8 input. Again third week, the first 2 weeks prediction plus the input of the whatever input we have taken before. So if you execute that, it will become more easy. I'll show you in the workbook. So that is the thing. And we can also do, like we have talked about convolution of 1D. We can also do convolution 2D plus LSTM, same thing. Only the thing is that the number of time series, the time steps we take as 1. Okay. And we use the length. You can specify. I have taken, say, 14. You can specify like how much you want to take. So samples is the number of samples you are taking. The time 1, time steps, rows and columns. So rows and columns and channels. Channels will again be like 1 or mostly we will put it 1, but the rows and columns is the number of you are having this data for, and the columns is the number of features you are putting it for. So that's how. This is that IBM paper using Watson paper using multiple time series. So how they predict this time by taking the input from this. So we are running out of time. I'll go to the workbook. So you can go through this, that how they combine different techniques. They use cluster, regression, as well as classification to derive a multi-step time series. It's a very useful website. They use it for measurement of different parameters, and you can go through this. That's why I put that different time series can be combined, and how they have done it with iterating and trying to predict different, like in terms of different lengths, they have tried to predict the horizon. This is a direct step application of multi-step time series, and you will also find multi-step time series getting used in supply chain. Suppose you have not known what is going to happen in my design phase, so you predict something on the design phase, use that data and predict how the it goes into production life cycle. So that's the IBM paper. I don't go into details. And then ensemble, this is another important thing. I will go to the workbook how much time it takes. This ensemble prediction, like based on the trends, you will understand what is the maximum predicted, what is the maximum value, what is the most likely. Here the curve is behaving like becoming a saturating, so it is the most likely predicted cells. And you can also use time series, like combine different models, like you do some resampling, you combine multiple LSTMs, and then go for a majority voting model. You can combine ADA boost, gradient boost, and get the result. So that is more of univariate on or multivariate. You can do deep learning, so you fill the missing values, outlier remover, some of the pre-processing you do, and then you see arima. You can also combine with regression models and neural network, and you can use all the techniques like arima, multiple regression, and neural network to get a weighted average of your time series prediction. So these are also there. It's not that ensemble modeling we are just using for normal credit card prediction or normal day-to-day predictions, but time series modeling also support different types of ensembling techniques. So these are more about that. Even you can combine with historical analysis, residual pause, historical event influence, like state and time. You can also use interaction of state and time, like three-dimensional predictions, video prediction. So use different mechanisms, combine them, multi-view ensemble learning. Okay. So our objective should be low variance and improve performance. So that is how we do very varied length based. That's why multi-step has come into picture, that you can use the step which I talked about 7 days. You can vary that every time. You can vary that, and you can use that for long term as well as short term models. 7 days I was using for short term, predict next 7 days, predict next 7 days, and then auto regressive models, like you can combine with do a weighted modeling, probabilistic modeling, and combine multivariate time series. And we use deep learning so that we can preserve maximum information from the input to the output without having any loss of your vanishing gradient problem. And these are some of the terms, like seasonal differencing. It doesn't have any effect. So this is, I have not done for arima, sarima, or Varmax models. This is left as a future work. And limitations. Arima also has limitations into, because it can learn nonlinear patterns. I also studied with Facebook. It yields a similar kind of prediction. It has two components of saturating growth model and a piecewise linear model. So one is the growth and one is the linearity. And also look at the term of non-random walk model. That is, it is more for random walk model is a very no term of time series. It works on non-stationary time series only with long periods of trends up and down. So let's go into now. There's deep learning things. So all the references are there. Slides are already uploaded. This is the GitHub, and I have specifically written 3 blogs. One on comparative study of arima, sarima, specifically with auto arima and normal arima. Then is this is the one, and these two are more on deep learning, single step and multi-step. So you can have a look. So we are running out of time. I can finish if you have time. I can finish this going through single step, multi-step deep learning models. So should I go? Everybody's okay? Yeah.
I just zoom it a little bit.
Zoom it. Okay, sure.
Yeah.
Okay, so this is single step prediction. So for whichever state you have to choose, you can choose it. So some of this libraries you will need it for your other thing, that the auto sarima, Facebook profit models, stats models. So these are, I just kept it imported. These are also a library for TS learn, SVM time series, SVR, unsupervised modeling. Okay, and now comes into TensorFlow, what we have talked about, that multivariate. That is the most important thing, and we have exogenous factors. Sometimes you may see that the number of tests are going up. We have seen some in the correlation plots that number of tests or ICU beds are going up in areas which are red zones. These are direct correlation factors. So in places where there are not, it's not going up, but in places there are. So you can also treat them as exogenous factors. Okay, some factors are apart from lockdown. Some of these factors, like how many tests are there, how many quarantine centers I don't think are every day increasing so much. So it was at a time it was constant, and again when there was a surge there was an increase. So everyday value there's one not an increase. So these can be also treated as exogenous factors. So we have talked about time distributed convolution 1D convolution. Import this necessary libraries. This is done with TensorFlow 2. Flatten bidirectional LSTM for bidirectional flattening the and also we have used convolution LSTM 2. Let's see, start date and end date, and there is the data is there in GitHub, so you can use that. And once you have this, these are the factors which I'm taking into account: the total PP, total tested, unconfirmed, tag people in quarantine. All these measures are there, but again, one thing, there's a limitation. The data which I got has more some of these factors which are rapidly changing for some of the states like Delhi, Maharashtra. So these yielded, I can visibly see the results, while some of the states like which are not so much impacted, at that time was West Bengal was not impacted. So these numbers were not changing. I'll show you how. I drop this column and then apply test positivity, change it to numeric data, and then just indexing. This is re-indexing. So every time you plot time series, you have to index on the date column. Okay, and then let's see what's happening. So bamboo, I couldn't, so I didn't get a license. Okay, so Kerala, there's not much change. I told you. So there's not much change. Kerala, I didn't get much data for that, but I got data for Delhi. So let's look at Delhi. Yeah, so Delhi, you see there are some changes in respect to some of the parameters here. Here some of the parameters. Here discharge migrated is regularly changing, and here is this total people in currently in quarantine beds and total N95 mass. These factors are changing in terms of everyday. This is everyday data. So here was 0 and then it changes. Here also there are data which are changing. 13 and then it changed it to 4.6 tests per thousand. So Delhi was more proactive, so I took Delhi to measure it. 132, then 456, 3-4 days is 113, 456. So there is some changes. So let's see LSTM basis. So series to supervised. So there is I took that what is the start date end date, so that I index on the current date range. Then series to supervise. So take the data, input sequence is t minus n. So every data has to be shifted in terms of 1, because here input is 1, output as we have discussed. And then append the data, like for every data you shift it, you have to put it into somewhere, right? And what is the name of the column? This is just the naming of the column. So just we have for say multivariate data, right? So many columns are there. So for this is the number of columns. So for the number of columns, everything, all the time shifted data is prepared, okay, and it is returned. And selecting the features which are relevant, and then we go and do a min-max scaling, because I told you sometimes you will see there are 100 recoveries, there are sometimes 2 recoveries. So I scale the data into 0, 1, fit, transform it, and drop this. What is this? This is another very important step. So this I have done manually, but later I have done with code. So this is number of 2 into number of features minus 1. Why I tell you? So you have say n features. So you have already n features, plus you have created n after time shifting. You have created another n features, which is the target. Okay. So but you are not predicting for everything. So the rest of the features have to be dropped. You are predicting for one value. If you are predicting for so many things, it makes sense. So if are you also going to predict there how many N95 mass are going to come up? You're not predicting, right? So all the n minus n features have to be dropped. So from column there are 22 features up in this data. So 22 and 23 is the 23 is the first one which we are going to predict. That is the active cases we are predicting here. So that is the column that we keep. Rest all columns at n plus 1 has to be 22 plus 1, 22 into 44, 45. So 45 till 45 columns has to be dropped. Okay, this is the important thing. And then you split the data and do a prediction and print. I'll come to this because this is a long thing. And then after you have done the prediction, calculate the error, but you have to inverse your transformation. Why? Because you have scaled it in terms of 0 and 1, so you have to do a inverse scaling. So you have to get it back in terms of hundreds or thousands or millions. So this is very important because you have done min max scaling or apply standard scaling. Inverse transform, compute the actual data, RMSC, compute it and plot it. So this was my prediction. Okay, it doesn't look so good. And now let me expand this. It's huge. So the loss I have taken, so this is huge. So you can, when you download the notebook and look at it, I will just current output. I will just hear this. Okay. So this is, you see, this is the scale prediction, and this is the actual prediction. I've got, but I've done inverse scaling. I found out the correct. So it's increasing 330,000 cases that time, done in June. So this is the prediction value. April till April data, till 4th of May data, and the whole of March I've taken for training, and the rest this is prediction, 1.5 months prediction. So same thing, you have to drop it. And then when you do bidirectional step, this is the important step. When you test the data or train the data, ensure your shaping is proper. This is another very important thing. Otherwise, your network deep learning neural network, that LSTM or CNN, is not going to understand. It expects the data in terms of samples, steps, and features. And features is, we have 22 features. We have one time step, as we've talked about. We are not doing video processing, and the samples, like the number of data points you have. Every day's data point, every day is one sample. So if you have 35 days data to train or test, that is your, this one, 0 samples. Okay, same thing, that is the bidirectional LSTM. It looks better than single LSTM. Then stacked LSTM. Then stacked LSTM is nothing but, I think, hope you can see, is LSTM after LSTM, return sequence is true. So I add 2 layers of LSTM. It's a regression problem. It's no classification, no sparse categorical entropy or categorical entropy. Dense unit 1, plot it, predict it, reshape it. Before predicting, you have to reshape it. Okay, test data, print the shapes. Initially I was also learning. So print the shapes. Shapes are proper. So again, I'm not opening it. I have printed a lot of things. And then you have for scaled LSTM, multi-layer of LSTM. What is the inverse scale? Okay, this is the one. By LSTM is still better than multiple stacked LSTM. So this is normal from 0 to 1. The scaled prediction, you have to inverse scale it, get back the actual values. Then CNN, do it. Only the thing is, this is changing and the shaping is changing. So CNN after samples timestamps features. So that has to be done properly. Okay, CNN doesn't get good results. And then you have LSTM plus CNN. This is a convolution once time distributed layer, but we have talked about. Okay, and the same thing. This
will be okay.
Yeah.
I think we'll be ending the session now. Is that?
Yeah, sure. Yeah, you can check the GitHub, and this is the fine thing. And same thing we have with deep learning with multistep. Okay.
So we have a question for you. Is that how to start with Kaggle? Have you worked with Kaggle? You have some advice for the viewer how to start with Kaggle?
Yeah, check the notebooks. I have used Kaggle, but I don't put my notebooks into Kaggle because I have some timing constraints that for me to learn at this stage, Kaggle is not that much useful. But for beginners, it is of course useful. So start looking at what people have done. Take up some notebooks and try to do some other things from new libraries. Check out open source. What are the new libraries coming out? Put, and in Kaggle, you have to be more explicit in writing the steps how you have done it. So everything steps to be explained and proper figures and everything to be done. when you execute each and every step. So it's more of a, your notebook should explain everything what you have done, and there should not be anything that is left to the viewer to understand.
Okay, thank you so much for spending and giving us such insightful session today about time series analysis, and it was so good having you. Thank you so much for joining us. Any last words you would like to say to our viewers?
I think you can build more good insightful models using, if you're thinking still thinking of COVID-19. There are many things happening. I did finish in June, this one. So that time it was just not much enough data available. If you get more data, lockdown, vaccine, what is the impact? Utilize these models and develop. I would love to see the results.
Okay. So thank you so much everyone for joining us today, and we'll meet again next Sunday with another meetup. Until then, enjoy your Sunday. Bye.
Bye.